Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Section 3. Pretreatment and Post-treatment. As always, let's look at the content of this section. First, in this lecture, I present type of pretreatment. Then, pretreatment for membrane processes will be discussed, that how to select a suitable pretreatment to control substances and parameters such as colloidal fouling, biofouling, organic fouling, scaling, control of undesirable gases such as carbon dioxide, hydrogen sulfate, control of iron and manganese, pH and temperature control. In the next lecture, also post-treatment for membrane processes will be discussed, such as disinfection, corrosion control, and removal of dissolved gases and volatile compounds. In the end, the exercises for selection of pretreatment and post-treatment in the membrane processes are presented. Membrane system components. A schematic of a typical membrane system has presented. Components in a typical system include pretreatment, membrane units, product post-treatment, and concentrate post-treatment if required. First, I begin with pretreatment. Pretreatment for membrane processes. Objectives and requirements. The primary objective of pretreatment is to make a feedwater compatible with the membrane. Pretreatment is required to increase the efficiency and life expectancy of the membrane elements by minimizing fouling, scaling, and degradation of the membrane. Prior to feed pretreatment, the characteristics of the feed required to be analyzed in terms of various physicochemical parameters such as pH, suspended and dissolved solids, total hardness, dissolved oxygen, conductivity, specific solute concentration, chemical oxygen demand, biological oxygen demand, and etc. to ascertain the selection of one or more suitable pretreatment methods. Another important trend towards reducing the load on the membrane for water treatment is the integration of two or more pretreatment strategies to improve the performance of ultrafiltration, nanofiltration, and reverse osmosis. You can see in this figure common studied reverse osmosis pretreatment technologies in the past 10 years. As shown in this figure, ultrafiltration, coagulation, flocculation, and microfiltration are the three technologies that have been most studied by researchers as reverse osmosis pretreatment methods. In fact, ultrafiltration and microfiltration as pretreatment of reverse osmosis is gaining more and more popular in recent years. Coagulation and flocculation has long been used as a pretreatment method for not only reverse osmosis but nanofiltration and other technologies as well. Before discussion on the types of pretreatment, let's look at the treatment processes. In this slide, a list of treatment processes that are applied for the wastewater treatment has presented. Physical processes such as clarification, screening, aeration, filtration, flotation, degasification, and equalization. Chemical processes such as chlorination, ozonation, neutralization, coagulation, adsorption, ion exchange, and advanced oxygen process. Biological treatment processes such as activated S-Slash system, trickling filtration, ponds and ligands, aerobic and anaerobic processes. The physical-chemical treatment processes are also applied in waterworks. Of course, there are some differences in the applications and operation. Types of pretreatment. Pretreatments depend on the application and fit characteristics classified to physical, chemical, and biological pretreatment. Physical pretreatment. Solids not only can easily lead to blockades in membranes, but also can blockage plant components such as pipes, valves, and fittings. In multi-stage water treatment plants, the first stage is usually to remove solids by physical pretreatments for this reason. This can be implemented according to the following three principles: gravity, buoyancy, and particle size. The easiest way to separate solids is by sedimentation. In the sedimentation tank, the solid particles fall to the bottom due to gravity and can then easily be removed with S-slash scrapers. Effective sedimentation requires laminar flow conditions in sedimentation tank. Typically, sedimentation in water treatment plant followed by coagulation and flocculation, but before filtration system. In wastewater treatment plant, mainly used as primary and secondary clarification. Solids with low settling velocities cannot be effectively separated by sedimentation because this would require very large sedimentation tanks. In this case, flotation processes provide a sensible alternative. The basic principle is still the same. Gas bubbles attach themselves to the bottom of the solids and drive the solids to the surface. Once there, the floated solids can be removed with special scrapers. Flotation processes differ mainly in the way the gas bubbles are produced. In water treatment, the most commonly used method is dissolved air flotation, or DAF. In this process, a partial flow of the treated water is saturated with air under pressure. The air-saturated water is then passed back to the inlet region of the flotation tank as circulation. An expansion valve is located just before the inlet to the flotation tank, which causes the water to suddenly re-expand to atmospheric pressure. This expansion causes the dissolved air to form fine bubbles. Filtration mechanism is also the same with membrane filtration, as I have already explained it in the previous section. Chemical pretreatment. This table summarizes chemicals that are commonly used in the conventional pretreatment process of the source water prior to reverse osmosis membrane desalination. These chemicals can be categorized into coagulants, flocculants, scale inhibitors, acid, and oxidizing agents. Coagulants and flocculants are mainly utilized to enhance the settlement of suspended solids in the feedwater to achieve higher removal rates. The addition of scale inhibitor is to increase the solubility of dissolved salt such as calcium carbonate and magnesium sulfate to reduce the extent of scaling. Oxidizing agents such as chlorine is used to eliminate the growth of aquatic organisms, aiming to reduce biofouling on membrane surface. It must be noted that some chemicals are required to use continuously in order to maintain the performance of reverse osmosis membrane by minimizing fouling. Conventional treatment methods in general are well accepted in the reverse osmosis desalination plants for several decades, but they are not without drawbacks being used in the reverse osmosis pretreatment. Studies have indicated that conventional treatment require high chemical usage, large footprint, large manpower, and high operating cost. With respect to treated water quality, conventional pretreatment that consists of media and cartridge filtration does not provide definite barrier to the suspended particles and colloids. Thus, in order to address these issues, microporous ultrafiltration membrane as pretreatment method becomes the prime option in many new seawater reverse osmosis plants installed worldwide. Of course, it has to note that although ultrafiltration membrane is very effective to remove particles, colloids, dissolved organics, and microorganisms, the presence of high concentration of dissolved organics in the water source can easily cause fouling due to the surface adsorption. Therefore, chemical treatment with coagulants prior to ultrafiltration process can be beneficial to not only reduce ultrafiltration membrane fouling, but also to improve permeate quality, leading to reduced cleaning frequencies of reverse osmosis membrane. Nevertheless, the successful coagulation and membrane filtration are quite sensitive to coagulant doses because doses above or below the optimal dose is likely to negatively affect the permeate flux. Biological pretreatment such as anaerobic reactors, activated sludge system, aerobic biofilm reactors that are most common processes in wastewater treatment and also can be applied as a pretreatment for membrane bioreactors. You can study these processes in the concerned references such as the books in the biological wastewater treatment. In this part, I am going to recommend the most common solutions for controlling the main substances and parameters that cause the problems in membranes as we have already discussed in the previous section. These substances and parameters such as suspended solids which cause colloidal fouling, microbes which cause biofouling, organic matters which cause organic fouling, inorganic compounds such as calcium carbonate which causes scaling, carbon dioxide and hydrogen sulfate which cause corrosion, iron and manganese which cause precipitation and scaling, pH and temperature. Pretreatment to control colloidal fouling. As you know, colloids which cause turbidity in water and wastewater form a cake in the membrane surface as colloidal fouling. Typically depends on the membrane material. The limitation of suspended solids concentration or turbidity is recommended by manufacturers, but generally a range between 1 to less than 0.2 NTU is recommended for the prevention of colloidal fouling. Turbidity is measured in NTU, that is nephelometric turbidity units. The instrument used for measuring that is called nephelometer or turbidimeter. If you are going to select a pretreatment for membrane filtration include microfiltration and ultrafiltration, strainers or bag filters with a range of 100 to 500 micrometer are recommended. Suspended matters depend on the size can be removed using bag filters but not colloids. For this reason, in high concentration of the colloids, it is combined with coagulation and clarification because colloids have a negative surface charge and using coagulants such as aluminum sulfate, flux are formed and through clarification and rapid sand filtration can be removed. For nanofiltration and reverse osmosis, cartridge filters with a size range between 1 to 25 micrometers and for groundwater 5 micrometers is recommended. I have taken these photos to show you the pretreatment filters after some months of operation. But it has to be noted that these filters have to be cleaned using washing or replaced to the prevention of damage on the membrane. Pretreatment to control biofouling. Pretreatment methods to control biofouling depend on source water quality, type of membrane system, membrane tolerance to disinfectants such as chlorine. Source water has to be considered because, for example, in groundwater, you have no or less microbial fouling, but surface water systems require continuous control. In fact, as I have already said, the origin of the biofouling is microorganisms such as microbes. Microorganisms can be removed using disinfectants. For this reason, if you have biofouling potential in the water source, you have to select a membrane material that has a high tolerance to disinfectants such as chlorine. In lecture 4, we discuss it, but as a review, if you remember this table, the most common materials for reverse osmosis and nanofiltration are cellulose acetate and TFC. Cellulose acetate can tolerance up to 1 ppm chlorine, and TFC has a bad tolerance to chlorine, and this is the main drawback of these membranes. The reason for the TFC is that the thin or top layer of this membrane is a polyamide material. And as you can see in this table, polyamide has a very low oxidant tolerance. On the other hand, the best material in case of biofouling potential are inorganics, which have a very high tolerance to disinfectants. Some pretreatment methods for microfiltration and ultrafiltration, such as periodic chemical cleaning, backwashing, chlorine, or UV disinfection. For reverse osmosis and nanofiltration, chlorination, dechlorination, such as sodium disulfate, sulfur dioxide, to remove the chlorine residual prior to the membrane, UV disinfection, and dual membrane system. Pretreatment to control organic fouling. The origin of organic fouling is natural organic matter and synthetic organics. The main source of natural organic matter is in surface waters. Pretreatment for reverse osmosis and nanofiltration used to remove natural organic matter and synthetic organics. But there is no direct correlation between total organic compound and fouling. However, the concentration bigger than 10 mg per liter total organic compound is problematic. For microfiltration and ultrafiltration, backwash and cleaning frequencies. In parallel, coagulation, flocculation, sedimentation, powder activated carbon or granular activated carbon, lime softening efficient as pretreatment. In this figure, as a conventional method to remove natural organic matter, as well as colloids and suspended matters, in the first step, after injection of the coagulant on the pipe, using a stirrer, mixing and contact time increases to the formation of the flux. In the second step, a part of the flux is settled on the bottom. Adsorption of polymers as a flocculant and bridging called flocculation and precipitation with entrapping of particles is done. Then, in the clarification, formed flux can be settled. Pretreatment to control scaling. As we have already discussed, the salts that most commonly form scale are calcium carbonate, calcium sulfate, strontium sulfate, barium sulfate, and silica complexes such as silicon dioxide. Calcium carbonate, which can exist in the form of calcium and bicarbonate ions in industrial water, groundwater, and seawater, is the most common type of alkaline-based scalant, in particular in reverse osmosis membranes. It can be reduced through softening and dealkalization processes in combination with sand filtration or microfiltration, which I am going to explain more in the next slides. Calcium sulfate, strontium sulfate, and barium sulfate scaling can be reduced using antiscalant. To reduce silicon dioxide scaling, it is recommended to reduce recovery. We will discuss about the recovery in the next section. High lime softening as precipitation process can reduce the concentration. Addition of silica antiscalant, increase of feedwater temperature and pH can contribute to reduce scaling. Softening and dealkalization for removal of calcium carbonate. Reducing the total hardness, alkaline earth ions calcium and magnesium is softening, and reducing the temporary or carbonate hardness is dealkalization. As you can see in this table, most relevant processes as pretreatment, especially for reverse osmosis systems, include precipitation with sodium hydroxide and calcium hydroxide, acid addition, and ion exchange. In this lecture, I explain sodium hydroxide and calcium hydroxide, and for more study, I have uploaded a PDF file as Appendix 1, and you can download it from the website. Dealkalization with calcium hydroxide. As you can see in this equilibrium, to remove total hardness include calcium and magnesium and also temporary hardness as carbonate and bicarbonate. In reaction with calcium hydroxide, calcium carbonate builds up as a product and then can be removed using filtration processes such as rapid sand filters, microfiltration, or cartridge filters as a pretreatment for reverse osmosis. One of the effects in this process is in the presence of iron and manganese, the ironing and demanganization can be done simultaneously. Dealkalization with sodium hydroxide. As you can see in this equilibrium, the product of dealkalization with sodium hydroxide is calcium carbonate, sodium, and water. In comparison with calcium hydroxide, at the same hardness reduction, only less than 50% reduction of bicarbonate can be done. Because with calcium hydroxide, in the removal of 1 mole calcium, 2 mole bicarbonate can be removed, but with sodium hydroxide, 1 mole bicarbonate is removed. It can also be used in combination with calcium hydroxide. This process is not recommended for the reverse osmosis system due to increase of sodium concentration, which is one of the main advantages. Pretreatment to control carbon dioxide. Once the concentration of carbon dioxide is high, especially in groundwater or wastewater treatment, because of its corrosive characteristic, it has to be removed or reduced using deacidification process. Deacidification is removal of carbonic acid in order to bring the water into the state of chalcocarbonic equilibrium together with an increase of pH, as you can see in this equilibrium. In groundwater, as a result of biodegradation of organic material in the soil, the concentration of dissolved carbon dioxide in seepage and groundwater is often higher than the equilibrium concentration related to the chalcocarbonic equilibrium. If there is no calcium carbonate available for the reaction with carbon dioxide, or if the contact time between water and carbonate is too short, the seepage water and groundwater cannot reach the state of chalcocarbonate equilibrium. As a consequence, the water contains a carbon dioxide excess, which gives the water an aggressive or corrosive character. Therefore, The carbon dioxide excess has to be removed from drinking water before distribution. Calcium carbonate can be removed using mechanical deacidification or chemical deacidification. In these figures, two different processes of mechanical deacidification have presented. Chemical deacidification also can be done with sodium hydroxide, calcium hydroxide, calcium carbonate, and half-burned dolomite. Pretreatment to control hydrogen sulfide. If the purpose of treatment is for drinking water, hydrogen sulfide has to be removed. Some of the problems of hydrogen sulfide, such as unpleasant odor, corrosion problems on some metals, tarnish or discolor problems, stain laundry and bathroom fixtures yellow or black, discolor beverages, and alter the appearance and taste of cooked foods. Usually, chemical cleaning is ineffective to remove it. As a physical cleaning method, membrane degasifiers can be applied, as you can see in this figure, or some methods. Pretreatment to control iron and manganese in reverse osmosis and nanofiltration. Actually, if reduced water which contains iron and manganese ions comes in contact with oxygen, intensively colored flux of manganese oxide and iron hydroxide will be formed. Some problems that caused by dissolved iron and manganese, such as problems during drinking water distribution due to blockage of pipes, colored and particle containing water is not accepted by consumers. Water is not suitable for many industrial and other commercial purposes. Pretreatments for iron and manganese removal. To remove iron and manganese, at first it has to be oxidized with air, chlorine, or other oxidants. Then, with granular media filtration, microfiltration, or ultrafiltration, it can be filtered. The oxidation equilibrium has presented for iron and manganese. Depends on the application and concentration. Methods such as cation ion exchange softeners, acid addition, and inhibitors can be applied. In this reclamation plan that recommended for industrial reuse, you can see de-ironing and demanganization in the chain. First, oxidation is accomplished in the flotation process. Then, using filtration process, oxidized iron and manganese are removed. In parallel, coagulants added to the flotation process to attach the suspended particles and form flux, and in sedimentation tank will be settled. Pretreatment to control pH. To control pH as pretreatment, both pH range of membrane material and desired pH in order to reduce fouling and scaling have to be considered. As we have already discussed the membrane properties in this table, in the selection of membrane material, the range of pH value has to consider. There are some limitations for the organic membranes, but inorganics can act from 0 to 14 and there is no limitation. For example, in reverse osmosis and nanofiltration, polyamide as top layer of TFC membrane can act in the range of 4 to 10, but cellulose acetate between 4 to 6.5. In the selection of the membrane material, you must consider these limitations as we have already discussed. In microfiltration and ultrafiltration, the organic materials such as polysulfone, polypropylene, and PVDF can act in the pH range between 2 to 13, but inorganic membranes nearly any pH. Pretreatment to control temperature. Temperature has influence on altering membrane material characteristics, change of solubility, and permeate. In this table, you can see the maximum temperature of membrane materials. For example, cellulose acetate membranes deteriorate from hydrolysis with higher temperatures, or polyamide membranes deteriorate from compaction with higher temperatures. On the other hand, viscosity and density of water increases at lower temperature. As a consequence, production rate declines. Change of solubility also has some influences. For example, change of solubility of soluble cells and silica result in the limitations of the design recovery of membrane desalting process. Or at higher temperature, scaling potential based calcium carbonate increases, but in a lower temperature, higher scaling potential for other cells can be taken place. Exercise. Typical reverse osmosis and nanofiltration pretreatment processes for 4 types of water sources have presented. Please tell me your reasons for the selection of these pretreatments. In the next lecture, lecture 10, we will also discuss about it more. Now this lecture finished. Please study the appendixes 1 and 2 to learn more about the softening, dealkalization, and deacidification processes. Let me know also your solutions for this exercise, and you can also download it from the website. Please send your solution to me by email or using the website. In the next lecture, we will discuss about it more. Thank you for your attention.